In this video, we're going to take a look at ionic bonds and compounds, how they're formed, what their structure looks like, and what kind of properties that then gives them. So when ionic compounds form, we have an anion and a cation. Anions again being the negatively charged ions, and the cations the positively charged ions. And even though they're composed of these charged particles, these ions, they're electrically neutral overall because they combine in combinations that balance each other out. And those ionic bonds are really strong, just like magnets, between a positive and a negative charge, holding together those particles in one crystalline structure. And ionic compounds are always formed between a metal and a nonmetal. Metals that like to lose their electrons and make positive cations, and nonmetals that like to gain electrons to make negative anions. Again, an ionic bond is an electrostatic attraction, that oppositely charged positive cation with a negatively charged anion combining together, sticking to each other, giving them a really strong bond. We see that in sodium chloride, better known as table salt, where the sodium cation and the chloride anion combine in a 1-to-1 ratio to make a crystalline structure that you then sprinkle on your food. The reason why they get together in that 1-to-1 ratio is sodium, being in that first column with the alkali metals, has one valence electron, which it will gladly give up. Chlorine in the halogen family with 7 valence electrons, group 7a, wants one more electron to be like argon to complete its outer shell. So they combine in a 1-to-1 ratio to then get noble gas configurations. We look at ionic compounds by their formula unit, which is a ratio of the cations to anions that make that compound neutral. What is the smallest whole number ratio of ions to make that compound neutral? So within that formula, we see both what types of elements are in that compound and what ratio they are combining in. Again, the smallest whole number ratio, because ionic compounds will continuously just keep building larger and larger and larger crystalline structures due to the positive cations and the negative anions being attracted to each other. It can just keep filling out and making larger and larger and larger crystals. So within that crystal, we have a formula unit, again, that lowest whole number ratio of ions that makes the compound neutral. So here we see two different ionic crystalline structures. This first one here is sodium chloride. Again, we see one sodium to one chlorine balancing out over and over and over, and you see the opposite charges next to each other, those green chlorines next to the yellow sodiums. So they're never next to each other where they would repel, opposites attract, positive, negative, positive, negative. And here we see water, which is a molecule, and they're all separate individual particles. There isn't a repeating crystalline structure like we see on the left with sodium chloride. They're all their own separate entity, those H2O molecules. And because of this, we see some pretty interesting properties of ionic compounds. Most ionic compounds, again, are crystals. They are a solid at room temperature, and they also have really high melting points due to it. It's a repeating three-dimensional pattern. Again, like we saw with the sodium chloride, you just keep adding more and more of those positive and negatively charged ions in a three-dimensional pattern. Left and right, front and back, top and bottom. And as we said, they do have a high melting point, and they also have the ability to conduct electrical current, which we'll discuss in a moment. It has to do with those positively charged particles that make them up and the attraction between them. Here's two other ionic compound crystalline structures. So it doesn't just have to be a 1-to-1 ratio like sodium chloride. On the left we see aluminum oxide, but once again you see the blues and the reds and the blues and the reds separated out on the diagonal, where you never have two of the same charged particles next to each other, and it just keeps repeating over and over and over three-dimensionally. On the right we see sodium sulfide, 2 sodiums for every 1 sulfur, but once again there are no like charges next to each other. Those yellows and the blues within the sodium sulfide crystal do not match up. So ionic crystals have what we call a coordination number. going back to that sodium chloride, it has a coordination number 6 because there are 6 oppositely charged particles around each sodium and each chloride ion that make up that crystal. If you look at that cubic pattern of sodium chloride, there's one in front, one in back, one to the left, one to the right, one up top, one down below for every sodium chloride crystal. And as we said earlier, ionic compounds, they also can conduct electrical current when they're melted or also dissolved in water. Due to being made up of those charged particles, they have the ability to pass electrons. And electricity is the movement of electrons. And since they have the ability to take on and give up electrons with those charged particles, they can conduct electrical current. So you can't just put electricity into a salt cube, but when you melt it down into its molten state, or when you dissolve it into water, it allows you to conduct an electrical current. Again, here we see sodium chloride, you have this coordination number 6. If you look at that sodium ion right in the very center, again, up above there's a green chloride, down below there's a green chloride, to the left there's a green chloride, to the right there's a green chloride, in the back there's a green chloride, and in the front there's a green chloride, so 6. Every single ion within the sodium chloride crystal structure will have 6 oppositely charged particles next to it. And here is a picture of molten sodium chloride. Again, those charged particles. And up top we see a battery with a voltmeter showing how the electricity is flowing within that molten sodium chloride. And the charged particles can move to the anode and the cathode within it.